Ciao friends! In this video we are going to see how different rounding errors can affect different data types in DAX. I know, this could be not a good news for you because you expect that a computer always do the right math, but we will see that there are cases where actually what we obtain could be not correct if we look at the result from a human point of view, but is perfectly acceptable for the machine because of the data type we chose and the calculation that is involved with those data types. So we're going to see what happens when we have integers, currency data type, which is the fixed decimal number in Power BI, and floating point, which is the decimal number in Power BI. And we will discover that the choice is not simple. We cannot say this is better than something else because depending on the data model you have and the calculation you have to do, you have to pay attention to these details. Let's start with the demo. So we're going to see several examples using our classical Contoso database that we see in this diagram. There is nothing particular here, but I want to point your attention to a few elements. The fact that we have columns of different data types. We have the quantity. Let's take a look at the data type of the column. We have the quantity, which is an integer number, even though it is called whole number in Power BI. We have the net price, which is a fixed decimal number, which is a currency data type in DAX, but it is called fixed decimal number in Power BI. And finally, we have a copy of the net price called net price decimal, and we store the same amount in a decimal number, which is a floating point. So we're going to analyze the different type of rounding that are used when we manipulate operation, arithmetical operation and aggregation over these columns. So we already have an article that describes what happens at the data type when we apply different arithmetical operation, like the sum, the subtraction, the product and the division. And you can see that by multiplying, for example, a currency by another currency, we get a decimal. So there are cases where the result, the data type result is not obvious. And of course, if you just look at the data type of the result, you already have an idea about the different representation of the numbers that you can have. But what we want to focus is in this video is what happens when the result of the operation cannot be represented in an accurate way in the final data type of the destination, and what is the behavior that we can expect. So let's start looking at some operations. So I have DAX Studio connected to the model, so we will start doing some simple operations that actually don't require the use of the data that we have in the model, but then we will also use some aggregation of the data in the model using the columns that we have just seen. So let's start with something simple. So what happens when we have the integer data type? So we will see one data type at a time. So we start with the integer, which is called whole number in Power BI. And the idea is that the integer data type has 64 bits to represent the numbers. And the largest number that can be represented is a number that has 63 bits because the additional bit is the sign, positive or negative. What does it mean? Let me just copy this number here. So if I want to see a large number that can be represented by an integer, I can just evaluate the number that you see here. So 5 with 18 zeros. So it is an easy way to write a number. We can see the number, and this is the number that has 18 zero after the 5. So I don't know how to read this number. It's certainly the biggest number we can represent. And actually the number works. But I know that we are at the boundary now of the range that can be represented in 64 bits. So what happens if we go over the limit? If I sum twice the same number, which you can imagine is the same thing that will happen if you aggregate a column and you go you produce what we call an overflow. You try to obtain a number that is over the limit of the range limit of the integer. What happens? Well, you see that we have no error at all, and the result has a number that in this case is negative. This is expected. The overflow of an integer in the computer system does not produce an error, but I mean, it could produce an error actually, but in this case, it doesn't produce an error and just produce a wrong number. So you have to be aware that if you're going to represent a number that is too big, you could have this type of problem without any error. Same happens for the subtraction. The same happens for the multiplication. And for the division, this is not going to happen because the division is always a floating point number. So if you divide two integers, what you get as a result is a floating point. We can see this in the table that we have here. So an integer divided by an integer is a decimal, which is a floating point value. And in that case, the overflow is not produced, even though we will see that we have other rules that we have to pay attention to for the floating point. Because of course, you might have an expression that then is aggregated in a sum, for example, and so you sum the result of another operation, so the result of the operation involving a division between two integers is a floating point, so at that point you have to reference the behavior of the floating point. So this is the result of the arithmetical operation with the integers, and this is true also for the aggregation. So if you aggregate a number and the result is outside of the range of the integers, you have to expect an overflow that doesn't raise an error, just produce a wrong number, a number that is not the right one. So let's move forward and let's see what happens when we have a fixed decimal point, which is the currency data type in DAX. The currency data type or fixed decimal number is stored internally as an integer, but it is like a number that is then an integer number that is then divided by 10,000. So the internal representation is an integer, but we represent this way a number that has up to 4 digits after the decimal point. So the original number is multiplied by 10,000 and stored into an integer, which means that the internal operations are always applied to integers. And so we have the same behavior of the overflow. The only difference is that we have a reduced range of values that can be represented into a currency. For example, we can repeat the same operation by using 4 digits less in the integer part. So I use this number that if I execute this number, I see the number without any error. This is the same number that I wanted to obtain in this representation. I'm forcing to, sorry, not an integer, I want to see currency in this case. And I run this code, and this is the value of the currency. It is still working. But what happens if I sum 2 of these numbers? We have the same behavior of the integer. Now it is just the same number that we have seen before divided by 10,000. So the sum has the same behavior that we consider because internally it is still an integer. And for sum and subtraction, because the same thing can happen with the subtraction, we have this behavior. For the product, we don't have the same behavior. Why? Let's take a look 1 second to the diagram here. So you see that in this table, if we multiply currency by currency, the result is a decimal. So the result of the product is not a currency, which means that we're not going to get an overflow apparently, but we have other possible consequences. For example, let's start from the currency with another currency. If the result is a decimal, because this is the more interesting part, if the result is a decimal, it means that the result can actually be represented in a floating point, which has a larger number of a larger range of values that can be represented, but it has a lower number of digits that are significative, which means that a rounding could be in place and produce a different result for the multiplication. Before we look at this result, just a quick mention, if we have a currency multiplied by an integer or a currency multiplied by a decimal, we have a currency as a result. What does it mean? Well, this is interesting because if you multiply currency by an integer, the result never produces an overflow error. So even though the product between a currency value and an integer value could generate a number that is outside of the range, that does not produce an error. We can try to see that. If I go back to my DAX Studio, I multiply this by 2 with an integer, because this is the same operation like I do the sum of these two numbers. So if I run this code, you see I have the same error. If I multiply by, let's say, 3, of course, this could be misleading because at a certain point I will see a positive number which is actually lower than the original number. So pay attention. When you multiply currency by integer, the overflow could be not immediately visible and still produce a wrong number. So this is something to pay attention. Now, what happens if we have the same multiplication, but instead of multiplying the currency by an integer, we multiply the currency by a floating point that in this case is represented as a double. So this is the same operation that didn't produce an error before. If I run this operation, bang, I have an error. And the error says that the result of the conversion arithmetic operation is too large or blah, blah, blah. In reality, what is happening is that the result of this multiplication that involves a double produces a number that, even though it is computed correctly, cannot be represented into a currency, because the destination data type of currency by decimal, currency by floating point, is still a currency. And so because it is still a currency, it has to be represented in that range. In this case, we could see the overflow error, and so this stops the calculation. So this is something to keep in mind. Depending on the result you want to obtain, you might want to decide to do the conversion to a floating point just to see the overflow. But in case you don't want to get the overflow and you want to get the result, you can just try to multiply two currencies together. And what happens at this point if we try to multiply the two currencies? Well, if I use a currency again here, if I run the code now, you see that the result is correct. Look at that. If I put 5, the result is correct. And actually, we have the good number. But at this point, the problem is that, pay attention, because the number of significant digits of the result is limited to 15, which means that it's not that the other are not present. It's just that the number could have a rounding error or a rounding operation that removes some precision compared to the same number applied to, for example, two currencies that don't have the same problem, as long as you keep the number within the range of the valid results. In order to see that, I have prepared a particular calculation. So let's see if I can show you this. So this is a number that I can store in a currency data type. And again, we are always toward the limit of what we can do. But actually, it is a big number. It has many digits. You see that we have probably 17 significant digits in this number, even though 4 of them are in the decimal part. And we multiply this by 111 using a double. Okay, so the result, currency multiplied by double, is a currency. In case we had an overflow, we will get an error. Otherwise, the result is a currency that has the range of values of a currency. So we run this code, and we see the result. Sorry, I run this again. And this is the result. So this is the number we have in the result. Now, let's try to write the same operation. So I copy the same operation in the following row. And in this case, I use a multiplication between two currency data types. In this case, the result will be a floating point, but the floating point will be rounded to using by the 15 significant digits. As you see, we have more than 15 digits here, so what happens? Let's try. You see that now we have the same number, but in reality this is because I used the same column with the same data type. So let's use two different columns so that we have two different data types, one for each result. And so if we compare side by side, value 1 is the result of this calculation that produces a currency data type, and this has more significant digits in the result. And this is, and you also see that the number has been rounded to 2 decimal points for the auto formatting of DAX Studio. Actually, could disable it, which is probably better. And let's remove the automatic result, former result. So if I run this code again, now we have the 4 digits. I prefer to keep the automatic formatting later, but this is just to show you that the number, the actual number, has 4 digits. In this case, we have only the integer part. And not because we have as a result an integer in this case. In this case, the result is a floating point, but the floating point has only 15 significant digits. And this is the reason why the number has been rounded to the closest integer, because this was the number of digits that were possible to represent in that number. So let's restore the automatic format result. Let's execute this again, and let's see the numbers. So we have the different numbers in this case. As you can imagine, this creates a problem. So let me just graphically represent the different data types we have in the results. So this returns a currency, which is the column value 1. This returns a double, or a floating point, which is the value 2. You can imagine that the problem is that what happens if you compare these two numbers? If you get the same, if you produce the same arithmetic operation in two different parts of your code using different data types or different conversion in an intermediate step of the calculation, then when you try to compare the two numbers, these two numbers are not the same. These two numbers are different. So an equal to operation will produce false as a result. Clearly, we have seen what happens with very big numbers, but what happens when we have smaller numbers? Well, in this case, so we see that in this case, we may say, well, we like the fact that we have a currency by a double, because the result is a currency, we have more digits as long as the range is correct. But in reality, when we have a calculation that, for example, introduces small numbers, we could have other type of differences. So let's remove this, and let me copy another type of calculation where we start with this calculation. So we use 4 digits, 1, 2, 3, 4, 5 in the decimal part of the number. This is a currency, so this is maximum number of digits we can produce. And we multiply this by 0.1. Now, multiplying by 0.1, the result should be 0.12345. But now we ask the result to have 5 digits after the decimal point. And of course, if the result is a currency, because in this case the result is again a currency, this cannot be represented in a currency, and so the result is 0.12. This is a case where we want to go here and see the value displayed without the formatting, or we can disable the formatting, because we have to do this for a number of times now, and we will only see decimal values. And here we go, we have only 4 digits. So the number has been rounded to the closest number. So instead of looking at 0.12345, the result has been rounded to 5 in the last digits. What happens if we repeat the same operation and we just change this double to currency? So in this case, the result will be a floating point, so a double. And if I run this code, now you see that, let's remove this comma. We see that the value 2, the value of the second column, is actually including 5 digits after the decimal point. So in this case, if you need the precision of the number, you probably want to use the double in the result. As a data type of the result, because of course we have more digits, but this depends of course on the complete requirement you might have. Remember, we are using multiplication at this point, but keep in mind that the result of this multiplication could be summed in a measure. We will see later when I use sales amount with the result of the multiplication, this will be more evident. Now we talked about the multiplication, but what about the division? So I prepared a number of another example that I can copy quickly here, and we want to see this example 4 times. So let me prepare this. We want to see what happens if I divide a number that has 4 digits, the same number we have seen before, by 2 using the 4 data types we have available. Actually, the 3 data types we have available. Double. So we start with an integer, we try also the floating point, and we try with the currency. But we also want to try the division where the currency is at the denominator, and at the numerator we have a double. We cannot have an integer with the decimal part. So this way we see what happens when we have more or less all the possible variation of currency and other data types in a division. So let's execute this code. And let me comment what we have. Let's start from the first one. In the first one, we are dividing the currency by an integer. The result has to be a currency. And so because the result is a currency, it can only have 4 digits. We have as a result a number that has been rounded. So the 5th digit has been rounded to the 4th digit. What happens when we divide a currency by a double? The result is still a currency, and so as you can imagine, the result is still rounded. What happens if we divide a currency by a currency? Well, in this case, the result is a double, is a floating point. And this is the case where we have the result 0.61725. And what happens if we divide a double by a currency? We didn't introduce the double so far, but when the currency is at the denominator but the double is at the numerator, the result is still a double. So in this case, the result didn't lose any precision. Again, because we have less than 15 digits in the number that we obtain as a result. So far, so good. We have seen a number of multiplication. It's important to keep in mind that, I think in this table, keep in mind that when we have a currency involved, the currency produces a currency in the product when you multiply by an integer or by another floating point, whereas two currency multiplied together produce a decimal. So let's move forward, and now we can start doing something with the floating point. So the floating point is, in theory, a data type that is that has a larger range of values that can represent. And so we can have more complex numbers, but of course we have to keep in mind that with the double we have 15 digits. So in order to see what happens for these cases, we did the following. We have this number, which is a number that has 2, 4, 6, 8, 10, 11. We have exactly 15 digits here, which is the maximum number of digits we can represent with the maximum quality in a floating point. And then we add to this number, this small number, 0.0002. You understand that this starts to stretch the number of digits we have to represent to more than 15. We need 16 digits at this point, because we will have 1 here, but we also need to add 1 here, and we extend the number of digits required. And we also have the negative number to see what happens. Now, if you think about the operation, before I execute the code, if I use A plus B enters the result into an area where the range of values cannot represent with the maximum accuracy the number I want to show, then I subtract C, and because between A plus B I could have lost some accuracy, when I subtract C, which is the same value of A, I might not see B as a result. Whereas if I do this operation saying I subtract C, I do A plus C, and so I subtract the same value, the result should be 0 at this point, and then I sum B, then I keep the maximum accuracy. So my expectation is that the number I obtain in the first row could be different from the number I obtain in the second column, so in the first column and the second column, because we're using a row with 2 columns. Okay, so this is the expectation. Let's see what happens. Let's execute this code. And here we go. You can see what happens. The fact that you see, so the first number is, let's say, not correct. In reality, this number is close, very close to the original number we wanted to obtain, which is this one. The number we want to obtain is 0.0002, but because the floating point internally cannot represent in an accurate way more than 15 digits, what happens is that it doesn't completely lose the digit, because otherwise we would have seen a completely wrong number. We see a close enough number that is what we mention as the rounding error produced by the floating point. The floating point cannot represent the exact number and represent a very close number. Very close is a relative concept, because of course at this point you might say, well, but for this number the error is too big. I know, this is exactly the reason why we're producing this video, to make you aware of these problems when you do calculation with numbers in Power BI, in DAX. But this is a problem that exists in any programming language, to be honest. So it's not something that doesn't exist in other systems, but if you are not aware of that, you might make a wrong choice of the data type and see some strange, unexpected result that you could have avoided by using the right data type for your model and your calculation. So we can try to see what happens, what is the difference when we use currency instead of floating point in this calculation. So this is one case where we can see how the choice of the data type can be important. If this is a operation that I could expect in my model, in this case currency works better because I have more digits that I can represent, and so it doesn't matter whether I do A plus B plus C or A plus C plus B, the result is always the same. You see that the two columns produce the same result. So the idea is that it's important to be aware of these differences, because based on your data model, on the range of data that you have, and on the operation you have to perform on them, you can choose the right data type. Now, what is the impact of these differences with your model? Because what we said in a simple operation with three numbers is actually true also when you aggregate a column, when you aggregate the result of a multiplication. And this means that the order in which the rows are evaluated could apply a difference in the result. And so the same calculation, just because the data is analyzed in different orders, can produce different results. So let's see an example of this by looking at the model that we have seen before. So just let me recap what we have in the model. We have quantity, we have net price. Net price is a currency, fixed decimal number, and quantity is an integer data type. So we have an integer multiplied by a currency in the measure that we use sales amount. So sales amount is the classical quantity multiplied by net price, and we sum the result of this multiplication across all the rows of the sales table, depending on the aggregation we apply in the report. We created a column net price decimal that has the same value of net price, just with a different data type. So in this case, the data type is a floating point. Decimal number is the floating point, which is the double in the DAX syntax. We created a measure that we will create again in the report, but the measure sales amount decimal performs the same operation, the same calculation, by using net price decimal. So you see that the result should be the same, right? Because we do the multiplication, the result should be the same. And if we look at the report, by looking at the numbers, they are the same. We don't see any difference at this stage. But let's try to go to DAX Studio and see what happens if we look at the number in a deeper way, not just the first two decimal digits, 2 digits after the decimal point. So I prepared an evaluate statement where, let me describe what I want to do. I want to filter just 1 month, let's say January 2018. If I go back to Power BI, January 2018 shows two numbers that are identical, so we see the same number. But if I apply this filter and I execute the evaluation of A, sales amount decimal, and then I sum sales amount decimal by date. Okay, so I compute the sales amount with the floating point number. In one case, as a single value for the month of January. In the second case, I want to compute this amount day by day. So I compute the calculation for each day of January. So we have 31 numbers, and we sum these numbers together in the sum x. The result should be the same. The result is the same if we look at the value in Power BI, in the Power BI report. But I will create a row where I show the value of A, the value of B, so the two measures, and then I show the difference between the two measures. It should be 0, right? And if A is equal to B, which should be true. Let's try. And as you see, there is a difference. Even though the numbers look the same, even though we display these numbers with 4 decimal points, which is the automatic formatting we have in in a floating point, there is a small difference between these two numbers. It's a small difference. It's something that requires 9 zeros before the 1, 6 that we see here. So it's 0, 0, 0, 0, 0, 0, 1 something. But this small difference is enough to fail the comparison between A and B. So this is the situation. Even for a simple calculation like this one, because we are comparing two floating point numbers, we should use a range of tolerance. So we should basically, instead of comparing these two numbers as identical, we should analyze the result of the difference that should be below a certain, maybe the absolute value of the difference should be below a certain tolerance that you can accept to analyze the two numbers, which is also slower, by the way, in terms of calculation. But the idea is that this is something you have to do all the times you are managing floating point values, because this is the nature of the calculation of the floating points that we have in a calculator. Just to show a quick example, if I used sales amount, the regular one, which is an integer multiplied by a currency, so an integer by a fixed decimal price that produces another currency, another fixed decimal price. If I execute the same example, you see that there are no problems at all. So again, we see that it's difficult to make a decision because there are pros and cons in all the options. If we use the currency, we have a better precision, a better accuracy. If you use the floating point, we have a bigger range of values we can represent, but also for smaller numbers, we have a lower accuracy, and we might need to check the difference instead of the absolute numbers when we do when we want to compare one number with another. Now, the problem we have seen with the decimal is more evident if we do a calculation where we repeat this month by month. So what I'm going to do, I'm going to create the same report that we have seen in Power BI. So I'm creating a report where for each month I compute the value of sales amount. But in this case, I compute always sales amount decimal. In one case, I compute sales amount decimal as a normal value, as a regular value. In the second case, I simply use the month to date. Yes, I'm using a time intelligence calculation, because guess what? The time intelligence calculation, this dates MTD, is producing a list of dates in the filter, which requires the engine to compute sales amount decimal day by day, and then sum the result, because this is an additive measure. So it's a sort of optimization made by the engine to produce the result in a faster way. So let's format the code so that we can see this better with a larger font. So this is what I'm going to do. So I'm going to compare sales amount decimal computed for each month with sales amount decimal computed for each month with the month to date. So this is just this is the same number, of course, because we are still considering the entire month. And then just to check what happens, we compute the difference, because we want to see that whether the two numbers are actually the same or not. We execute this code and we comment the result. There are months where the difference is 0, which means that actually the two numbers are the same from any point of view, but there are many months where there is a difference. The difference is always very small, but exists. So the difference is not visible if you look at the visible digits in the report, but the difference is enough to fail the comparison between the two numbers. And you see that this happens relatively often. So in case we use the result with a time intelligence calculation, we introduce an intermediate calculation that changes the sort order of the calculation and can produce different results. So this is something that we have to keep in mind. The presence of filters, the presence of iterators can alter the order of the operation. And even though you say, I'm using the same data type, I'm using the same calculation, you can still have differences because of a filter that has been applied to the report and is applied to a calculation in a different way for the floating point values. So conclusion, let's recap what we have seen. So we have seen that we have many choices available. We can choose, in particular, for decimal points, two different data types, currency and floating point, or fixed decimal number and decimal number in Power BI. The choice is not so easy because we can favor the precision, the accuracy of the currency, knowing that we can only have 4 decimal points, or we can extend the range of the values that we can represent by using the floating point number, but at the same time we reduce the number of significant digits that we use in the calculation, also obtaining different results if we do the same aggregation, the same operation with a different order. Which one is better? It depends. You have to make the choice according to your model and the requirements that you have. But in any case, enjoy DAX!